you may have wondered why the tree of Tangle's theorem is called a tree of Tangle's theorem, because all it ever talks about is a nested set of separations with certain properties. So let me indicate a little more clearly how nested sets of separations give rise to trees and vice versa. How trees can describe nestedness. So let me start with a real tree. So this is a graph theoretical tree. Now, and we can put partial ordering on its oriented edges as follows. We say that an oriented edge E is greater than another oriented edge, F, say. Well, if it's behind F in the right way, like in a Q. And I think you all understand this definition, except it's anything but precise. So it's a fun little exercise to actually make this precise. The way to make it precise is to say that if this is UV and this is XY, then the edge E oriented from U to V is greater than the edge F oriented from X to Y if the unique path in T between this two set and that two set starts at V and ends at X. Well, that's only a formalization. Nobody can remember that. So what you remember is that, right? The tree is something like this, and this is greater than that. Okay, so that's obviously a partial ordering. It's transitive, right? Because all these paths in trees are unique. If you have another one here, then this is also greater than that. So that is a partial ordering. And the unoriented edges, if you like, are nested in our earlier abstract sense of admitting comparable orientations. Right? Remember, we said that for separations, graph separations, we call two graph separations nested, or a set of graph separations nested, if any two of them have comparable orientations, if it's possible to orient them so that one is bigger than the other or the other way around or whatever, right? And this is clearly the case here. If you pick any edge and any other edge, you can orient them so that one is greater than the other. In fact, you can choose which one you want to be greater. So this can be oriented towards that, and this away from it. Then this is going to be greater than that, and converse makes some orientation of this, namely the inverse orientation greater than the inverse orientation of that. So they're nested, the unoriented edges are nested in this sense. And the vertices of the tree correspond to the consistent orientations of the edges. So an orientation of the edges obviously is what you think it is, and what it was in the flow chapter. So for every edge you pick one of the two orientations, and consistent is again what we had for separations. So if one edge is greater than another edge, both oriented, and that is in our orientation, then the inverse of this must not be in the orientation. right? So if we orient the entire set, then obviously this one must be in the orientation. So in this sense, in this case, consistent is identical to being closed upwards in the entire space of oriented edges. Right, so why is that the case? If you have a vertex of this tree, say this one here, then it gives rise to a consistent orientation of all the edges, namely, just orient them all towards that vertex, right? T. And that is consistent. If you had an inconsistent pair, what's that? That's two edges pointing away from each other, just as it was for set separations. If you had an inconsistent pair, they couldn't both be pointing towards T. So orienting all the edges towards some chosen vertex T is a consistent orientation of the entire set of edges. And conversely, if you have any consistent orientation of the entire set of edges, then you don't have that. So you follow the arrows to some sink until you get stuck, until you are at a vertex where every edge points towards you, maybe at a leaf. If you keep following them and you end up at a leaf, fine. So if you have any orientation, follow the arrows and you get stuck at some vertex with every edge pointing oriented towards you. And if that orientation was consistent, then this vertex is unique, because all the edges will be pointing towards that, otherwise it will be inconsistent. Right, in that case, so this consistent orientation points to some vertex, and then it is indeed the consistent orientation that this vertex gives rise to, as we had it earlier. So the vertices correspond to the consistent orientations. And there's one bit of notation that we need. So for every node or vertex T, ft with an arrow on the f is the set of all edges at T oriented towards it. Right, so this is a set of oriented edges. Namely, at T, all the incident edges oriented towards T. That's Ft, and we shall be using that later. Okay, and while we're at it, maybe that can come later. No, let me define it now. So while we're at it, an S tree, so S is some set of separations of our graph G. An S tree is a pair of a tree, and alpha is a map from the oriented edges, all the oriented edges of the tree, to the oriented separations, the orientations of separations in big S. It doesn't have to be surjective, it doesn't have to hit all of them. It doesn't have to be injective even, but it has to be compatible with the two partial orderings that we have. We have a partial ordering on the oriented separations, and we have a partial ordering on the oriented edges of the tree, and it has to be compatible with that. So every edge, say this edge here, gets mapped to some separation in S, and if we orient this edge, then there's a corresponding orientation of that partition, and indeed there's exactly one, because we also ask of alpha that alpha commutes with inversion. So when you flip, alpha maps an oriented edge to some oriented separation, and it then maps the inverse of that oriented edge, the same edge oriented the other way, to the same separation oriented the other way. So that's this here. So if an illustration for this first point would be that we have an oriented edge E here that maps to some separation, say S A comma B, something like that. And then if we have another oriented edge F as earlier, then if that is T, the separation CD, then we require that E oriented like this, being greater than F oriented away from it, should be matched by the images under alpha in that S is oriented in such a way that it is greater than, in the partial ordering of oriented separations, the image of this edge F arrow, which is CD. So we would have A being a subset of C and B being a superset of D. Okay, so yeah, that's an S tree. And notice that the image of the edges well, we have alpha only on the oriented edges, so I have to write it in this way. Call that N is nested. Right? Because alpha preserves the partial ordering. So whenever you have something, whenever you have two edges with comparable orientations, then these orientations map to oriented separations, and if they're comparable in that the first was bigger than the second, then the image of the first is going to be bigger than the image of the second. So in particular, the unoriented separations underlying these images are going to be nested too. Right? So formally, I would say that a set of this form, i.e. a symmetrical subset of this, oriented, containing both orientations of any edge of which it contains at least one orientation is nested if the underlying set of unoriented orientations is nested. That's the same thing expressed with arrows rather than without arrows. So when we have an S tree, then the separations it displays by mapping to them, so we're talking about the image, not about the entire S, are going to be nested. And conversely, we'll have a converse too, but let me just make two more remarks here. And one is that alpha of this set here, the incoming edges at a node of the tree, what are they? Well, if, no, I can say generally they, so we saw that a tree, a node of a tree corresponds to a consistent orientation of the entire set of edges of the tree, and then of this consistent orientation of the entire edge set of the tree, Ft here is precisely the set of minimal elements. So let me just indicate that like this here. And what I want to get at is this, that this is a star of separations. What's a star of separations formally? It's any set of oriented separations with the property that if you take two of them, each is greater than the inverse of the other. Okay, so that's obviously the case for this star, tree star, at the node T, oriented towards T, right? This edge with this orientation is greater than the inverse of that, right? In this ordering that we had on the edges of, or oriented edges of the tree. So we borrow that property and make it into a definition for separations, for oriented separations. So once more, a star of oriented separations is any set of oriented separations with this property that every element of that star is greater than or equal to the inverse of every other. Okay, and it takes a moment's thought to see that this is symmetrical, but it is because the when we reverse the partial ordering, a relationship remains true if we also flip the two orientations. Okay, and now we can give a converse of this, which says that when we start with any nested set of separations, so for every nested set n of separations, I don't really need the S here, there exists an S tree. I could call this an N tree now if I wanted to get rid of S. With image precisely my n, so every nested set of separations comes from an S-tree in this way. We can construct for any nested set of separations some tree and invent alpha so that this tree with this alpha becomes an S-tree whose image just happens to be the nested set that we started with. And how would you do that? So we have to write down the tree, right? So what would you take as the vertex set of that tree? We have to cook one up, so we're free to define anything as the vertex set of that tree. Well, we want this tree to do this job later. So in particular, the vertices of the tree, however we define them, should correspond to the consistent orientations of its edge set. And the edge set should correspond to the given nested set that we have. So we'd better make the nodes precisely that, the consistent orientations of n. Fine. And it's a little more interesting to come up with a definition of the edge set. So if we define the vertices in this way as consistent orientations, when are two adjacent? If we are in the tree universe here, and we look at two consistent orientations, nodes, that are adjacent, how can we express that in terms of the consistent orientations, which is all that we have here? If we have two adjacent nodes, then how do the two consistent orientations that correspond to the two nodes differ? Well, they don't differ on these edges. They all point inwards. They only differ on this edge. So the consistent orientation that corresponds to this node here must orient this edge that way, and the consistent orientation of the edges that corresponds to this node here must orient it the other way. So we can try and define the edge set as something like pairs of consistent orientations that differ on only one separation, something like that. But you have to do it precisely and so on. It's a fun exercise. Examples of S-trees, well, the tree decompositions, obviously. All right, so when we have a tree decomposition, it comes with a tree, and we look at the separations it induces, those separations that correspond, as in lemma 12.3.1, I think, to the edges of that tree. Those are separations of G, and we proved in lemma 12.3.1 that they're all nested. Or we saw that in there. The lemma says more. And so that's an example of an S-tree that makes visible the nestedness of some set of separations, namely those induced by the tree decomposition. But a tree decomposition comes with a lot of overload. It has all these bags, and we have to define the bags and so on. So what I wanted to get to is how to visualize our trees of tangles. Now, I'm using the term trees of tangles in a way that I haven't formally introduced, namely for the nested set of separations that these theorems, the tree of tangle theorems, produce. Right? So if you have that nested set of separations, you can find a tree. That displays that. In this way. So you start with the nested set of separations, distinguishing all the tangles. You cook up a tree like this, which is an S tree for this set of separations. An S tree with image this set of separations, and now the separations, they had different orders, right? So we had some low-order separations that already distinguished a few tangles. Then maybe we had the next level let me just write k equals 1, 2, and so on. Of course, in reality, there'll be some other numbers. The point is they're increasing. So when we allow higher orders, then we can distinguish a few more tangles with the separations of order up to or less than 2. And so on. The color code is for yellow k equals 1. I coded these edges that correspond to separations of order less than 1. Right? That's the color code I want, because then the yellow edges here correspond to separations that have order less than 1, or more generally, some k, and all the k-tangles can be distinguished efficiently by some edge in our entire collection. This edge, obviously, if it distinguishes two k-tangles, has to have order less than k, so it has to have a color up to that k. And these nested sets n index k of separations less than k are displayed by minors of this tree formed by contracting those edges that have a color bigger than that k. Right? So we get a sequence of minors all very nicely encapsulated in the same picture. So we have T1 is a minor of T2, is a minor of T3, and so on, where Tk is an S tree displaying Nk being those separations in our nested sets that the tree of tangles theorem returned that have order less than k. All right, so you get them all nicely in one tree. Okay, and if you want to, you can turn all these into tree decompositions. So I daren't write the tree decomposition into that picture because it'll get confusing. But if you turn an S tree into a tree decomposition, you have to define the bags, but that's easy. You just have these separations. If you want to define the bag for this node here, you have f of this node here, and you take the intersection of the big sides of all these separations here, and that is your bag. So you get something like a few big bags for k equals 1, and then maybe they get split up into smaller bags. These get split up into yet smaller bags, and so on. And if you want to, you can then later get one overall tree decomposition by removing the bags that got subdivided. Into smaller bags. Okay, something like that. Okay, so that's really it about trees of tangles and how to display them. And once more, last chance for questions. No. Then I now want to get on and to the second fundamental theorem about tangles, and that's the Tangle-tree duality theorem, which is in the top corner there. The TTD stands for Tangle-tree duality. There's lots of duality floating around in tangle theory, so this is the least formal. It just means that you have either one or the other, basically, and you can't have both at the same time. So both of what? Coming, that's what it says there. Given K, you either have a k-tangle in G, or if you don't, you have an SK tree over, I have to tell you that. Over stars that are in curly big T. So when you have an S tree, then this is over a set curly F. Curly F, when you see a curly F, it's usually indicative of something forbidden. So that'll come in a moment. Just think of it as any set, because the substance will come now. This is over F if for every node alpha of Ft is an element of this F. Okay? So we basically collect together all the images under alpha of these FTs. Here, these are stars of separations. And if all these stars of separations that we get at nodes are in some curly F, then we say that this S tree is over curly F. Curly F is allowed to be bigger. Okay? And in the Tangle-tree duality theorem there, you have a curly T with a star. Remember, curly T is the tangle set, right? That's the set of all 3 sets or up to 3 sets of oriented separations such that the union of the small sides makes up the entire graph G. Right? That's the definition of this big curly T in the definition of tangles. Right? Those things that were forbidden in a tangle. And T star is simply the stars in there. Okay? So, this theorem tells us that we have something else if we don't have a k-tangle, namely an SK tree over the stars in big T. I'll show you the easy direction of that equivalence. That's the implication from right to left. If you have an SK tree, suppose you also have a tangle. I want to get a contradiction. Then you have this SK tree. And this tangle is a k-tangle. So it orients the entire SK. In particular, it orients all these separations these edges correspond to. That defines an orientation of the edges themselves. And now just follow the arrows and find a sink. Then look at the separations that correspond to the FT. Those form a star of separations, and they also form a subset of your tangle because all the oriented separations here are in that tangle. That's how we got the orientations of these edges. But at the same time, since this S tree was over T, the image of this oriented star, so this star of separations, is not only a subset of the tangle, it's also a subset of this big T. And it is a star. But that can't both be true. So k-tangles don't have subsets in here. Okay? So clearly, we can't have a k-tangle and an SK tree over T star at the same time. And the substance of the theorem is that these certificates for the non-existence of a k-tangle do in fact always occur. So whenever we have the situation that our graph does not have a k-tangle, then we can find an SK tree over T star, which shows this non-existence in this very simple way. Then let's prove it. We'll need one more thing, and that's for the other implication, and that's the uncrossing lemma. So you might have found it sort of dubious or suspicious that in this proof of the easy direction, we found a subset of the tangle that wasn't just in big T, but was in fact a star, from assuming that there's a K tree. So that could make one suspicious, unless something called the uncrossing lemma is true. What does the uncrossing lemma say? Every consistent orientation of Sk that avoids T star is, in fact, a k-tangle, so it avoids all of T. Okay, so k-tangles, we know that k-tangles are consistent. That was one of the early observations. Also, k-tangles don't have any subsets in T, let alone stars in T. So a k-tangle clearly is a consistent orientation that avoids T star, and the uncrossing lemma says the inverse is also true. If we have a consistent orientation avoiding T star, it even avoids T. So proof uncross any set in T star, in T that isn't already in T star. So I'm giving this consistent orientation a name, tor, and I want to show that if it avoids stars, then it avoids all of T. Now we're saying suppose it doesn't avoid all of T, suppose it has a subset that's in T, let's find a subset even in T star, another subset. And the way to do that is to say well, consider two crossing separations in sigma. Say one is to the right and the other is up. Then I claim we can replace it in this same set sigma we can replace one of the two separations in here with a greater separation, strictly greater separation, that keeps the modified sigma in T, so that the union of the small sides is the entire graph. That's the assumption for sigma as it comes, and we want to modify the sigma by replacing one of these two separations with a greater one, so that the modified sigma is still in big T, and it's also still in the tangle. And we can't do that infinitely often in a finite graph. So there's only finitely many separations in Sk, and if we keep replacing some of them, one of them with a greater, strictly greater one, we can't do that infinitely often. So that would do it. And which of these two separations are we going to replace, and what with? Well, let's look at these two corners. Right? Not those two, these two. Then by submodularity, since these two separations are both in Sk, one of these corners is in Sk. So we'll log this is in Sk, so it has order less than k. Well, but then we replace the vertical separation with the corner with a yellow like this. Okay, if we orient it like this, well, first of all, if it's in SK, Tor has to orient it. Since it orients vertical to the right, it has to orient this to the right. It can't orient it that way. That will be inconsistent. So this corner here, oriented like that, is going to be in Tor. And throwing this out of sigma and putting this oriented corner in sigma instead keeps sigma in big T. Right? Why? We have to show that the small sides still cover the graph. And what have we lost? Well, we have lost something here, right? The things on the left that are not up left. So we have lost some vertices here. We didn't lose vertices here, but we might have lost an edge there. Or indeed, we might have lost an edge there, or there, and so on. But all these vertices and edges are still in the bottom side of horizontal. That needs to be done precisely, right? But in the book, it is done precisely. The proof in the book is unreadable. So I don't use a picture like that because I don't want to wave my hands, but this is the way to do it. It's not unreadable, but it's elegant. Same thing. Right, so we can replace the vertical separation oriented to the right with the top right, top left corner oriented away from the corner to get another element, another subset in the tangle that is still in there. And we do that until we don't have any crossing pair in sigma, and then we have found a star in Tor that is also contained in T, so that's an element of T star. That's the uncrossing lemma. Okay, questions? No. Okay. In that case, we're ready to launch into the main proof. So, proof of Tangle-tree duality theorem forward implication. We show for some sets Tor plus, including the empty set, that one or two hold. So without knowing what T plus is, for the empty set, the statement that one or two holds implies what we want. Why is that? Well, forward implication, suppose there's no k-tangle in G. Then there is no consistent orientation that avoids T star of SK. Right, that was the uncrossing lemma. If there's no k-tangle, there's no consistent orientation of SK that avoids T star, because then it would also avoid the entire T, as the uncrossing lemma says, and therefore be a k-tangle. Right? So for T plus the empty set, one fails. Okay? One says there is a consistent orientation avoiding that, but there isn't. If there's no k-tangle, then there isn't for this, the empty set. Then two holds for this, the empty set, that G has an SK tree over T star, which is exactly what we want to show. Okay, so that's a formality now. So notice that 2 is weaker than what we want to show. Right? We're relaxing the statement that we want to show that there's an SK tree over T star by allowing this SK tree to be over something bigger. So at the FTs, the images of alpha can be some other sets than those in T star. So we're weakening the assertion that we want to get, well, at least if this is non-empty. And 1 is stronger, a consistent orientation of SK, than being a k-tangle that has to avoid T plus as well as T star. Okay, but we don't need that now. We have done the formal implication, so it's enough to show for this relevant T plus that I'm going to define, which we have to make sure includes the empty set, that 1 or 2 holds. Now, T plus will depend on a set that I'm going to call O minus. And that will satisfy 2 things. It will be a set of oriented separations in SK. Let me just write this down. And it will have 2 properties. One is that it contains all separations of the form AV that have order less than k. All right? And is closed upwards under our partial ordering of oriented separations. Right? We'll be considering various such sets O minus, and each of them will give rise to T plus, to some T plus. And what is it? Namely, T plus is going to be the set of all singletons the wrong way round. So the inverse singletons of elements of O minus. Except those that we don't need because they're in T star already. So in order to enable T plus to be empty, which we need, we take away those that are already in T star, right? So we're considering the union of T star and T plus all the time. And we want to be economical about T plus, so we make T plus smaller by taking away those that are already in the union. Okay, and that's it. So T plus will depend on a given O minus. I could sort of put this there all the time, but I don't. There'll be another lower index in a moment, so that'll get too much. And so what are sk trees over T star union T plus. The additional elements of T plus are singletons, right? So when we look at the over condition, then the star of separations corresponding to this edge pointing there. That's a one element star, right? That has to be in curly F. Well, curly F now is T star, comma, T plus. What does it mean for that to be in T plus? And in particular, not in T star? Well, it means that this edge here corresponds to AB. Like this. Right? So the AB in O minus corresponds to this edge oriented away from that leaf. So basically we're allowing our SK tree to be over a larger set, but this enlargement of the set over which it has to be bites only at leaves because we're only adding singleton stars. So the stars in the middle here have to be in T star because T plus doesn't contain any singletons. And these are not okay. There's a formality here which I'll tell you out of sheer honesty, which is my doom, but alpha needn't be injective, right? So it could happen in principle that alpha of ft, all oriented towards this little t, has only one element. Oriented separation could in principle be this. So it's not clear that if we have a star of separations that is now allowed in the over star union T plus and wasn't formed, that it's not formally clear that this must be a leaf. But I'm going to gloss over this danger in the rest of the lecture, otherwise it would be unmanageable. But in the text, be aware that in the text, I'm not making this mistake. Right? So I'm telling you, this only applies to leaves. Okay, so we're relaxing the notion of an S tree over T star to an S tree over T star plus some leaves that are labeled with something else, namely what? With the inverses of elements in O minus. So O minus comes first, will come first. That gives rise to this T plus, which allows us some more leaves. It's like the petals proof of tree width duality. Remember that we allowed more things to happen in the leaves than were allowed at inner nodes of the tree. And it'll resemble the petals proof in other ways too, that will come in a moment. Okay. Right, so that's the definition of T plus. Let me for us all to remember, write down an immediate consequence of this, and that is that O minus is exactly the set of all AB in SK such that BA singleton is in T star union T plus. So that's not exactly the same as the definition here. So if we have an element of O, such an AB, right, then the inverse singletons are going to be in that set because they're going to be in T plus unless they're already in T star. So the inverse singletons are going to be in this union. For the converse, we have to think just for a second. If we have a set whose inverse singleton is in T plus, then the separation itself is going to be in O minus. Otherwise, the inverse singleton couldn't be in T plus because that's how T plus is defined. It requires this. Okay, but what if the inverse singleton is in T star? Then we have to think, what does that mean? It means that the left side covers G. So it means that this is in fact V. Then we have V comma A, but all the A comma V's are in O minus. So if this happens, then this is going to be in O minus too. Okay, so let's just keep this and remember it. And the next thing we may assume is that O minus is asymmetrical. So it's an orientation of some subset of SK. It doesn't contain both orientations of any one separation. And why is that? Well, easy. Suppose O minus had both orientations of some separation. Then I'd cough up an S tree over this as follows. So if this separation is, say, AB, and both AB and BA are in O minus, then this K2 labeled with this separation AB or BA, this is going to be an SK tree over T plus. Well, over the union, right? If A is contained in B or B contained in A, then it could also be in there. Right? Because both orientations are in O minus, that means the inverse singletons are in this by star. Questions? Okay, so we know now, or can remember, that O minus is an orientation of some set. Those are the separations, the unoriented separations underlying O minus. Right? the S in Sk that have an orientation in O minus. I denote that by S minus. Okay, and now I think we're ready to do the induction. Induction on the number of separations that are not oriented by O minus. And it starts when this is 0, so it starts when O minus orients all of Sk. Since O minus is closed upwards in Sk, it's consistent, right, because it's also asymmetrical. So it can't have two orientations oriented away from each other, two separations oriented away from each other. They couldn't both be in O minus, because if this is in, then by closed upwards, that has to be in as well. But if this is in, then this cannot be in by asymmetrical. So is consistent. And now let's check that 1 or 2 holds. So if O minus avoids T star and T plus, then 1 holds and we're happy. If not, then O minus contains, has a subset in T star a union T plus. So unless we're done, it has a subset sigma in T star union T plus. But now we can construct an Sk tree. Namely, we just draw a star with as many edges as sigma has elements, such that these edges get labeled with the elements in sigma. The oriented separations in sigma should correspond to the edges oriented towards that center of a star, which I'm inventing. So I claim now that this is an S tree over this. That's only true at this center, because there alpha of Ft is indeed sigma, and sigma is in that set. So that's fine. How about here? Well, these are this situation. All these oriented things are in O minus, right? So the over condition here is satisfied by T plus, unless this happens to be a separation of the type A, V, in which case it's in T star. So it's certainly in T star union T plus. By the way, T plus was generated from O minus. We did precisely that to make this true. Right? The singletons of inverses of O minus, those are precisely those that have to label these leaves. We artificially put these in T plus, so that this would be an SK tree over T star union T plus. Okay, so that's the induction start. For the induction step, S minus isn't the entire SK. So O minus has failed to orient at least one separation. So we add orientations of elements of SK minus S minus. And I wrote orientations of elements because we're going to do it twice. And we're going to do exactly what happened in the petals proof. So we'll apply the induction hypothesis twice. We'll be getting two S trees, and we'll merge them into one big S tree that satisfies two along a common, well, something like a common leaf. That's sort of the outlook, since you know the petals proof. So how do we choose these? We do it twice. Choose U1, W1, and U2, W2, maximal in SK minus S minus. So I don't want them to be oriented yet by O minus, so they shouldn't be in there either way. They should both be maximal such that O1, W1 is bigger than the inverse of the other. So if they're both maximal, then obviously this can't be bigger than the other. But we can have this. So how do we do this? Well, in two steps. First, we just take any maximal element of this set. Right? Amongst all the separations that haven't been oriented by O minus, take an orientation of one of them that is maximal. It has lots of stuff that are smaller. Take one that is as small as possible amongst all those that are smaller than this. Then flip it and call the flipped thing U2, W2. Right? Then this is maximal in this entire set, because if there was an even bigger one pointing that way, then the inverse of that would have been more minimal than this, subject to being smaller than U1, U, W1. So that's easy. So we have something like U1, W1 here, and somewhere at the end we have U2, W2 like this. Okay, now we add these to O minus. O minus I is going to be O minus union UI WI. Right? We just added to O minus, and notice that O minus I is still going to be closed upwards because we chose the greatest elements. Anything bigger, like this one, has been oriented by O minus, but it can't have been oriented this way by O minus because O minus is closed up. Then this inverse would have been in O minus as well. These give rise to Ti, and that's where I need the next lower index. Ti plus is defined just like T plus, except for O minus I rather than O minus. So in words, it's the singletons of inverses in OI minus, or O minus I, that are not already in T star. Okay? So T plus has actually grown this separation here, the inverse of that makes a singleton that was not earlier in T plus. So Ti plus has actually grown, not that we need that, but it's sort of reassuring to know that. What we do need for the induction is that O minus I is bigger than O minus. Okay, so now we imply the induction hypothesis. And that gives us 1 or 2. If one of them satisfies 1, then SK has a consistent orientation avoiding even this bigger set, T star union T plus I, then certainly avoids T star union T plus, and then we're home. So 1 doesn't occur, we're log. So both of them, for both I, we get an SK tree over this. If one of them doesn't actually use the new element in Ti plus, then it's an SK tree even over the old T star union T plus, and then we're happy again with 2, then we have 2. So we may assume they use them. So Ti has a leaf, Ui, labeled by the newly allowed singleton in Ti plus. Now, what's that? We added Ui Wi to O minus, so we'll have it Ui Wi here. The inverse Wi Ui made into a singleton labels this node, this leaf. Now, I'm pulling the wool over your eyes again by calling it a leaf. That's the same danger as earlier. We have to show it's a leaf. Right, all we know, sort of officially, that Ti isn't over this with the original T plus. That just means there exists a node whose over condition gives this singleton that we added, right? The singleton Wi Ui. And we have to show that this is, in fact, a leaf. It could be a non-leaf with all these edges, all labeled UIWI, 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 and so on. Why is that not possible? Well, I can give you a hand-waving proof of that. If we had UIW here and UIW here, then since this is a star, we would have UIW being greater than WIUI. That means that UI is a subset of WI. Well, that means, since it's a separation, if one side is a subset of the other, then the other is V. So UIWI would be UI, comma V. But that isn't T star. So we couldn't have added this. End of proof. That's why this is in fact a leaf. But make sure you check this. And it has a leaf UI like this. That goes for both I. And in fact, it has a unique leaf UI. Same proof. If it had another leaf up here, then they would be pointing towards each other, just as we now earlier had at the node T. So UIWI, UIWI would now be at leaves, UIW away from that leaf, UIW away from that leaf, and we'd have the same proof that UI would be a subset of WI, therefore WI would be V, and that would contradict the fact that UIWI is not an O minus. Not an O minus. Okay, so it has a unique leaf. That's good news, because now we're getting to the point where we can combine the two trees, and we have to check a few things, namely that they satisfy everything else that we want of an SK tree over T star union T plus. And that's where things go wrong initially. They are over the originally intended T star union T plus at UI, right? This is there's only one vertex whose label in the over sense is new, and everywhere else the old over condition is still satisfied. We have U1 here, U1 W1, and we have U2 W2 here. And now let's choose X1, X2 as a separation in SK. I'm not bothered about this being in S minus or not. In fact, it's going to be in S minus, but don't worry about it. Of minimum order such that the picture is right. So such that U1, W1 is greater than X1, X2 is greater than W2, U2. So something sandwiched between the two. This is greater than that. And we choose something of minimum order between the two. So it might be U1, W1, or it might be W2, U2. They're both candidates, that's fine. But maybe we can find a smaller one here. And now we sort of morally consider just the two sides in G. And we're going to use the tree with I equals 1 to decompose that side, and we use the tree with I equals 2 to decompose that side, and then we'll fit the two decompositions together. But this is very, very dangerously wrong. So all separations we always consider are not separations just of a side, but always separations of G. But I'm going to define for each I alpha I prime by modifying any separation on which AI has defined an orientation. Aha. So that's alpha of something. Right, and then if this is alpha I of something, then this is going to be alpha I prime of something. I'm going to show you how to turn the images under alpha I into images of alpha I prime. So for that, I'll have to show you what to do with a single separation AB. So alpha I orients that in some way. And since alpha I has to be defined only on the separations that correspond to the edges of Ti, and Ui is a leaf, every other edge is labeled by a separation that is nested with UiWi, right? So if AB is the image of some edge of the tree, then one of the two orientations of AIBI, this one or that one, is going to be greater than U1, W1. Say AB is greater than it. But they are comparable because they come from, this comes from an edge in the tree, and this is a leaf in the tree, right? Well, okay. Now, I want to essentially transform this into a separation of the right-hand side. So I could choose this corner or that corner. And I'm going to choose this corner. So this is AI prime of E. If this was alpha I of E. But how can I formally distinguish this corner from that corner? Well, because I have to refer AB to this. Only one of the two orientations is bigger than U1, W1. And that one I take, call it AB, and then the primed image of the same tree edge E is going to be A union X1 versus B intersection X2. Okay. And now we need to check a few things. One is that alpha I prime maps the edges of Ti to Sk, so that this separation has order less than k. Why does it? Well, it smells of submodularity. Why does a corner have low order? Well, we have to show that this corner has big order, right? So how big? We want this, the order of this, to be no bigger than the order of AB, because we know of AB that it has order less than k, right? Otherwise, it wouldn't be in the image of alpha I, or alpha 1. So we want this corner here, the red corner, to have order what? At least order of xy, x1, 2, 1. But it does, because it was a candidate for the choice of x1, 2, 1, and this had minimum order for being sandwiched between the two. This is still sandwiched between the two, because U1 is a subset of this small side here, because U1 is a subset of A, and it's a subset of x1, and therefore it's a subset of A intersect x1. Brilliant, and similarly with the supersets. So the red separation, this corner here, was a candidate for x1, x2. It wasn't chosen, so its order is at least the order of x1, x2. Therefore, the yellow corner has order at most the corner of AB, and that is less than k. Brilliant. So that is correct. Then we need that we have an S tree, so that this respects and the partial orderings and commutes with the flips. Well, and you can just check it. There are some nasty details there, so do check it properly in the text. But we essentially derive it from the corresponding property of AI without the prime, obviously. But one has to see what happens, how these things change in this shift, as we call it, so that this respecting is actually carried over. And then we need that Ti alpha I prime is over T star union Ti star, as before. And again, that needs checking and isn't quite straightforward, but it's not so bad. And now, glorious finish. Once all this is done, we can merge our two trees. So the two trees are T1 has this leaf, that's T1, and T2 has this leaf, U2, and let's call these neighbors W1 and W2, and we cut this off, and we cut this off, use this T1 on here, and use this on there. What does it mean? Well, what does this separation U1, W1, what does that shift to? What's the prime version of that? Well, U1, W1 in this orientation is greater than or equal to U1, W1. So this is the orientation like AB. So U1 is, we take the union of U1, is gone, union of U1 with X1, which is X1, and the intersection of W1 with X2, which is X2. So this in the shift becomes X1, X2. And similarly here, this in the shift becomes X2, X1. So we have an S tree here, and we can join these. So imagine that this gets put over here, and then, not this. And this loose end of an edge gets merged into this loose end of an edge to make this green edge. Right, and now the only leaves that had a wrong label in the over sense have ceased to exist. And all the other leaves are the same as before. All that has to be checked. So the combined tree is now T alpha satisfies 2. It's an SK tree over the original T star union T plus, because the addition to T plus that came in the T plus i's have been cut away.